Okay, welcome back to the second talk of the morning. I'm really delighted to be able to introduce our next speaker, Scott Sheffield, who is a Layton family professor at MIT. He did his undergraduate studies at Harvard and obtained his bachelor and master degree at the same time in 1998. From there, he moved to graduate studies at Stanford, where he worked with Amir Dembo and obtained his PhD in 2003. He held postdoctoral positions at Microsoft, Berkeley, Institute of Advanced Studies, and then he started a faculty position at Courant Institute of the New York University. After a couple of years there, he moved to MIT, where he has been since 2008. He is a prolific researcher. His main field of study is theoretical probability. He is working on questions that come from statistical physics, game theory, analysis, or are intrinsic to probability. He made major contributions to a number of fields, including quantum gravity, Gaussian free fields, Schramm-Loewner evolutions, tilings, diffusion limited aggregation, game theory, partial differential equations, and Lipschitz extensions. He received a Sloan Fellowship, NSF Early Career Award, a Presidential Early Career Award. In 2006, he received the Rolo-Davidson Prize for his work on spatial models of probability theory and especially their relationship to stochastic Schramm-Loewner evolutions. He was an invited speaker at the International Congress of Mathematicians in 2010. In 2011, he received the Lynn and Michael Loeb International Prize in Probability, awarded at UC Berkeley, to recognize outstanding contributions by researchers in probability who are 45 or younger. In 2014, he was awarded Simons Fellowship in Mathematics, and in 2017, he received the Clay Research Award together with Jason Miller in recognition of their introduction of novel geometric combinatorial methods to study doubling properties of solutions to elliptic eigenvalue problems. So without further ado, I'm going to turn over the podium to Scott, who will talk about universal randomness in 2D.
Good, thank you. It's a great honor to be here, especially on the to commemorate Yakov Sinai's remarkable work. I think anyone who does anything related to mathematical physics or probability or dynamical systems has been touched by his work in some way. So I'm very happy to be part of that theme. Today I'm going to talk about probability measures on spaces of continuum objects, think like random paths, trees, or surfaces, where the measures are canonical in the sense that they're uniquely characterized by symmetry, and universal in the sense that they arise as limits of many different kinds of discrete objects. So much as you might say the sphere is the canonical convex shape, right? It has more symmetries than any other natural convex body. You might ask, what's the natural probability measure on paths? And well, Brownian motion would be one of the most natural ones. It has a lot of symmetries others don't have. But you can ask, what's the canonical probability measure on the space of trees? Or the probability measure on the space of two manifolds? So instead of just one object, a sphere, you can ask for a probability measure on a space of objects that's also characterized by symmetries. And objects like this have a long history in physics and mathematics. Often there are discrete objects that are easier to understand and simulate, but the continuum objects are more symmetrical. And proving that the discrete objects approximate the continuous ones is a huge challenge, and there are dozens of known and unknown results. And I'm going to try to give a general overview of this subject. So these are a few of the papers, just to show you that I actually have been involved on some papers. And this is a brief summary of the various objects that will come up during the talk. So if you can quickly commit that to memory, that'll help me a lot. Okay, so I'm going to begin first with a cast of characters. I'm going to introduce 4 objects: random trees, random surfaces, random paths, and random growth models. And then in the second section, I'm going to tell you the drama, how these 4 characters interact with each other. And we'll find that often in this subject, you can introduce a few of these characters rather easily, meaning you can maybe with just, one, 10 or 15 minutes, I can really explain rigorously what these objects are. But then, some of these relationships are actually very difficult to prove. And so there are some things that have taken us hundreds or even thousands of pages to really work out the relationships between them. So to start with, let's do some dynamical systems that doesn't involve probability. Julia sets. Who here has seen these pictures before? Okay, so most of you. Good. So yeah, I mean, you just look it up, Google Julia sets, and you get some of these pictures. So this is, think Julia, 1918, popularized in the 1980s. If you consider a map, phi of z equals z squared, then what does that do? This is a map from the conformal plane to itself. If you think about it, it maps the complement of the unit circle to itself. Right? It maps the unit circle to itself, but in particular, it maps the outside of the circle to the outside of the circle. Okay? And what happens if you apply this square map over and over again? I give you a point and you keep applying. You keep squaring it and squaring it and squaring it. Well, if the number I start with has complex modulus bigger than 1, the point drifts off to infinity. If it's smaller than 1, it stays bounded. Right? So now you think, what if K is another compact set? Can I construct a 2-to-1 conformal map from the complement of that K to itself? And so another set, let's say, I need to give you a set. So let's say this is a convex set, right? So imagine I take the complement of this, and I want a conformal map from the complement of this set to itself. Well, we all know how to do that, right? You take the complement of this thing, you conformally map it to the complement of the disk, then I'm getting photographed with this. This was just a spontaneous thing, I thought, to pick this up. I never thought it'd be, okay, here we go again, smile. Yes, so you map the complement of this to the complement of the disk, right? And then you apply the square map, and then you apply the inverse map to the complement of this. That will give you a 2-to-1 map from the complement of this to itself. Now, when I was a graduate student at Stanford, they actually had a complex analysis qual where we actually had to learn how to explicitly describe the maps, the Schwartz-Christoffel maps from like a triangle or a square or a half plane, and you had like so much time to do it, and you actually had to come up with it, the formula for it. And if you didn't, you couldn't get a degree from Stanford in math. So I actually was forced to do this at one point. And what you found is that if you had just a triangle or a square, it was doable. If you have something more complicated, like a rectangle or a 5-sided star or something, then you can't really, it seems more complicated. So you might think that the more complicated this square is, the more complicated the 2-to-1 map should be. But in fact, some of the most beautiful sets have the simplest 2-to-1 maps on their complements. And so what's the next simplest map after phi of z equals z squared? That looks like z squared at the infinity? What would you say is the second simplest thing? Okay, you're saying it? Z squared plus a constant, right. I mean, that still looks pretty much like z squared near the infinity. And so if you just take z squared plus a constant, you can let K be the set of points that remain bounded under a p iteration. And then just by construction, z squared plus constant maps the complement of that set to itself in a conformal way. And so this set, K, the set of points is called a Julia set. And so going back to this picture here, this set, the set of black points here, or I guess I can use my snazzy pointer. So this set of black points here, or the set of black points here, these are the set of points that are fixed by one of these polynomials. Also, sometimes they're dendritic, they look like this. Sometimes they have They look like a curvy chain of bubbles. And what you notice is because this map, z squared plus c, conformally maps this set to itself, that map is a 2-to-1 map, right? So if I were to take a little region here and apply the inverse of that, the pre-image of this is going to be 2 little regions that look more or less like this, because a conformal map looks kind of like the identity locally, like the dilation locally. So the pre-image of this will be 2 things that look more or less like it. And the pre-images of those will be 2 more things that look like that. And then if I take, say, the 10th fold pre-image, I'll get 1,024 little things that look very similar to this thing, up to some conformal map. And so you get this incredible self-similarity, which is what makes it so beautiful. So, and so our eye just picks up on all the symmetries and just sees this as kind of a remarkably beautiful thing. Okay, and so someone named Duality, am I saying that right? Anyone know how to pronounce? What's that? No one's going to volunteer a better pronunciation. Okay. So in 1983, he came up with this idea that you can glue 2 of these Julia sets together to make a sphere. And he has these things on his web page. So if this actually works, I'm going to click on this and it will take me to the web page. Click. It worked. Okay. And so here, this thing that says rabbit, rabbit, I'm going to click on this and click on this movie, and it will magically go full screen. Yes, here we go. And you're going to see these are 2 Julia sets. And you can imagine, what if you take the boundary of this Julia set and try to map it to the boundary of this one? Well, remember I said when I give you one of these sets, let's see, you can take the outside of it, and you have a conformal map from the outside of this to the outside of the disk. If you take a uniform measure on the disk and pull it back to here, that gives you a measure on the boundary of this thing. Okay? And so even if this were a crazy fractal shape, you would still have some measure on the boundary. And so if I give you another set that has a measure on its boundary, you can imagine gluing the boundary of that set to the boundary of this in a boundary measure preserving way to create a sphere. And, or you can imagine gluing the boundary of this to the inside of an annulus, the boundary of this to the outside, and letting the annulus shrink. And then gradually they would get closer together, and eventually you get a sphere in the end. And I want to show you the simulation of that, so let's just watch. Gradually these 2 things get glued together. The fractal structure becomes more apparent as it comes to the end. And now we have a sphere. Spin around for good measure. Voila. Okay. And now I want to show you another one where I take one of these dendritic patterns. So let's see if I can escape. Or let's see, I'll do a tab back over to here. Let's take another one of these things. So he has a whole bunch of them here. But let's do this one where we glue this time one of them is this dendritic pattern. Okay, so this has 0 volume. When I glue the things together, all the volume is going to come from this one. But this one, if you think about it, this point here is identical to a point on the opposite side. It's the same point, but it's 2 different places along the boundary. So that when I glue this tree to this, somehow the point that corresponds to this and the point that corresponds to the other side will be 2 different points over here, and they will get glued together. So in some sense, this is a fancy way of gluing this thing to itself. And, well, let's just see what it looks like. It's easier to see the picture than to have me explain it. Somehow this comes in. And when it's done, all of the area comes from these things, these big blocks. Okay, and that's that. Now let's go to a next one I want to show. It's what happens when you glue 2 of these dendrites to each other. Okay. So now here you're probably a little bit troubled because last time one of them had area and the other one didn't. But how can you glue together two things that have zero area and expect to get a sphere? Well, what's that? A space-filling curve. Ah, yes. So what's the curve? What's that? No, I'm not looking for I'm saying, yeah, the curve. No, I'm just saying that's right. The curve will be if you look at the boundary of one of these paths, the boundary of the tree here, or this tree here, when it's glued together, that interface between the two trees will be sort of a space-filling curve. So, so there's a path that where I just trace the outer boundary of this set, and there's a path where I trace the outer boundary of this set, and when I glue them together, I will get a path that traces a path within the quotient of these two objects. And that path is indeed a space-filling path on this topological sphere. Okay, and you really have to see it to believe that it actually works. So here we go. Okay, ta-da, it's a sphere. And it's becoming harder to see what's going on at this point, but I don't think we have good enough resolution on. But okay, so that's the idea. And but I want to point out that there's sort of a space-filling curve in here that has lots of fractal symmetries in it. Okay, so let's get back to this. And so when this was introduced, these sort of dynamical things, they were part of what became known as chaos theory. Words like butterfly effect, fractal, self-similar came in to the popular lexicon. And these sorts of dynamics with the chaotic properties, this is a big part of this is part of what Yakov Sinai has done, these various different kinds of dynamics. So this is one particular flavor of that. So now let's get to these characters. I want to really think, in this story, all these things were very deterministic. And I want to ask, what happens if we do the same story, but instead of, we have random trees that we glue together instead of these fixed trees, or random objects? What can we say? So first, what is a random tree? Well, this is the simplest thing to describe. So take a Brownian bridge. A Brownian motion is this random path. And we take the random path conditioned to stay positive over an interval, and then come back at the end. This is called a Brownian excursion. And then what I'm going to do is I'm going to draw these horizontal lines underneath this, and I'm going to glue. So I first just think of this path as a line in black. It's a curve. And I'm going to identify points on this curve with points that can be connected by a chord underneath the curve. So one way they say it is take the curve, paint the underside of the curve with glue, then squash the whole thing together, and then let it unfan out, and you end up getting sort of a tree. Okay? And if you find that hard to visualize, let me do a discrete version of this over here. I have one piece of chalk that I'm allowed to use for moments like this. So imagine I have a walk that goes up, down, up, down, down, up, down. Well, sorry, can you still see this? Did I? Okay. So if I have this thing, you can imagine that you now glue together this side and this side, so that these get glued, these two get glued, these two get glued, and you get a tree where there's a branch up, 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 and this. Okay? So when I glue together these two, these two, these two, and these two, I get this particular tree. And if I were to trace the boundary of this tree, I go up, down, 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 up, down. That's exactly this. So this keeps track of the distance from the root as you trace the boundary of the tree. Okay? So if you really get nothing else from this talk, you at least, this is a sort of bijection that you hear it once and you remember it always. That the number of, if you want to count plane trees, they're in bijection with excursions. And if you take the scale of this, so you have more and more edges and you rescale appropriately, then you would get some sort of a Brownian path mapping to some planar tree. Okay. All right. So, and this fractal It's very easy to describe, but as far as I know, it wasn't really formally described until Aldous in 1993 described the continuum tree, although obviously the discrete bijection was known long before. And realize that this object here, you can think of this tree as a random metric space. There's a distance function, how far down and up do you have to go to get from one branch to another. It turns out to be sort of root invariant. If you forget where the root is and then sample it somewhere else from the natural measure on this space, you can get some invariance under that resampling. It has a lot of beautiful properties, and it's the scaling limit of these discrete random trees. If you take the uniform measure on trees with n edges, it's a scaling limit. And so in some sense, this is the natural uniform random planar tree. It's a scaling limit of various natural discrete models you can get. And so this is what you'd say is kind of a big success story in the theory of scaling limits. This is a very simple and beautiful object. It's the scaling limit of lots of different kinds of discrete objects. You could do a variant of this where you replace simple random walk with anything else that converges to Brownian motion. And they're all going to give you some sort of a tree like this in the limit. Yes?
When you drew the example on the blackboard, it seemed somewhat clear how you would embed that in the plane.
Yes.
There's that picture up there. Is that supposed to be embedding the...
Yeah, right. So basically, in order to have this embedding, I have to keep track of a little information beyond just the fact that it's a tree. So I have to know that from each point, what's the... If something has 3 children, I have to know there's a first, second, third of those children. Because otherwise, this thing... I could write the same tree this way. Right? This is an isomorphic tree to this. But it's a different function if I start at this point. So basically, we would call this a plane tree where I have the tree, but together I have additional information, which is which children are first. Descendants tell you. I know who's going to inherit the throne, right? This is my tree of children, but I also know who's in line for the succession. So you think of it as, if you want to have this bijection, it's a tree together with this extra bit of information that you know how the children are ordered. So that's what I mean by a planar tree. Okay, so now what's the canonical random path? Well, earlier I said it was Brownian motion, but Brownian motion, it crosses itself. If you draw a 2-dimensional Brownian motion, it scribbles all over itself. What if you want a path in 2 dimensions that doesn't cross itself? So it turns out that there's a family of random paths in 2 dimensions that can plausibly claim to be the canonical 2-dimensional random path. It has a lot of very special symmetries. And these are what we call these SLE curves, or Schramm-Loewner evolution curves. So here's how it works. So for any domain D and any parameter kappa between 0 and infinity, I can draw a curve. And if I give you 2 points on the domain, you can draw a curve, a random curve from one boundary point A to the other boundary point B. Okay? And there's a parameter kappa that tells you roughly how windy the path is. The larger kappa is, the more this path will wind. Okay? I want to define this and argue that it's, in some sense, the canonical random non-self-crossing path. So I haven't defined it yet, but let me first tell you what properties I want the definition to have before I give you a definition. So the first definition is that if I give you any domain D and another domain D tilde, and I have a conformal map from D to D tilde, then the image of an SLE here is an SLE over here. Okay? And so that tells me that if I define it on one simply connected domain with one pair of boundary points, then I can use the Riemann mapping theorem to give you the definition on any other domain with any other boundary points. Because to define an SLE here, I just draw one here and then map it over. And that gives me an SLE here. So that's conformal symmetry. But the Markov property part is that I want to say, if I take this path and I observe it up to some stopping time. So maybe I follow the path until the first time it exits some ball or something. If I take the path up to that stopping time and then I draw that part black, so I'm just fixing this as given, and I ask, what's the conditional law of the rest of the path, given this path? That is, the conditional law of the rest of the path should be an SLE in this remaining domain. Okay? And the theorem by Schramm is that these two properties completely characterize this random path up to this one parameter, this kappa. Okay? And when Oded came up with this, there were a lot of models in physics where the path was believed to be conformally invariant. If you drew it in one domain, you should be able to map it to another domain, and it would have this conformal symmetry. And so he just kind of made the leap and said, well, all right, we need a continuum model that has this symmetry. What can it be? And he worked out that this was what it had to be, one of these curves he defined. And he gave an explicit construction, which I'm not really going to go through this because I wouldn't have time, but if I had 10 minutes, you would understand it perfectly. Okay, so it's a very simple way of just describing this path using a certain ordinary differential equation where you plug in a multiple of Brownian motion as the input, and this kappa tells you what thing to plug in. And it's a very simple way of describing the path. And what Schramm proved jointly with someone called Stefan Roda, shortly after this was introduced in 1999, was that when kappa is less than or equal to 4, this curve is a simple curve. When it's between 4 and 8, the curve bounces off of itself, but it doesn't fill space, and it doesn't cross itself. It's kind of like, you remember when we glued together those two fractals at the very beginning? The interface between those two fractals is a curve that hits itself but doesn't cross itself. So remember, because the thing was like this little tree of disks, and so when you come around to a pinch point and hit it on the second time, it's a different point. So here, this is kind of like a random version of that. It's hitting itself but not crossing itself. And when kappa is equal or greater than 8, it's a random space-filling curve. So it's like a random version of that space-filling curve we saw at the beginning. Okay? All right. So, and I just want to say quickly, there's a version of SLE called radial SLE where the path grows from the boundary to a center point. Okay? And I'm not going to say any details about this. I just want to say that, there's some extra formulas you can use to describe these things, which I won't go through. But let's just say there's a way of drawing these paths that look similar to the original path. Locally, they look the same, but they grow from the outside of a domain to the middle instead of from one outside point to another outside point. And here, this is what my co-author Jason Wilson drew in order to try to indicate a space-filling path. Does anyone see the space-filling path here? Well, it's a space-filling path parametrized by color. So if you start at the red and then you just go through the spectrum of colors, then this traces out a space-filling curve. And whenever you see a place here where it's clearly one color on the other side and different color on this side, that means that I filled up this region, and then much a later time I came back and did this. And when you see like a subtle gap, like one shade of purple and a slightly different shade of purple, that means I filled this up, and then at a slightly later time I filled up the other side. Okay, so so you can kind of see where all the boundaries, the whole thing's kind of encoded in this.
So colors are one-dimensional.
The colors are one-dimensional, that's right. So there's a one-dimensional color line, and as I go through that one-dimensional line, I trace the whole thing. Okay, so now random surfaces. Here's, start out with a strip of paper and cut it into 12 squares. And now imagine that you take some glue, and I start gluing boundary edges of squares to each other. Okay? Well, there are 12 squares here, which means there are 48 edges. And so how many ways are there to map, to combine, group these edges into pairs? What is it, 48 double factorial or something? Do people learn this? I mean, I guess I have 47 choices for this one and then 45 choices for the next one, or 45, something like that. Anyway, so there's some large number of ways to doing this. Imagine that you just choose one of those ways uniformly at random. Okay, so they call this the drunk quilt maker model sometimes, because if you're making a quilt by stitching together these squares and you're drunk, you might not actually match up the right things to the right things. You don't get a rectangular quilt. But now you want to imagine that you are at least sober enough to ensure that what you get is simply connected in the end. Okay? And you want it to be homeomorphic to a sphere. So an oriental. You know, there's maybe a blue side and a red side to the quilt, and you're not mixing up the sides. Okay. So if you choose a random orientable thing, that will give you a random sphere homeomorphic surface. Okay? And, or you can do it with triangles. And here, one of my co-authors, Bertrand Duplantier, decided to choose a random triangulation and actually make it with sort of an origami-like construction. And so this is, you could think of a bunch of triangles or squares glued together in some fashion. And this is someone named Marquette, who actually produced one of these random triangulations on a computer with a very large number of faces, and then took the, put it into some software that tried to kind of embed this in 3 dimensions in some way as a surface, and then map it in to give you a sense of what it looks like. Okay? And you can kind of see it. It's got this very weird fractal shape. It looks much rougher than an actual typical sphere would look like. Okay. So these random planar maps, as they're sometimes called, were first studied by Tutt in the 60s when he was working on the 4-color theorem. There are all sorts of variants. You can do random triangulations. Sometimes you put some extra statistical physics structure on them. So you imagine that it's a planar map together with a spanning tree on it, a special spanning tree. Or maybe it's a map, but at every vertex you give it a spin, which is a 1 or a -1. So you assign a 1 or a -1 to every vertex. What we call the Ising model. You could put an Ising model on your planar map. You can think of this map as a Riemannian manifold with conical singularities, because it's like a smooth manifold, except that if you glue together, if you're gluing together squares, and you glue together a number at a vertex that's not 4, then near that vertex it looks locally like a cone instead of like a flat space. Okay, but everywhere else it looks flat locally. It turns out that this thing converges in law as a random metric space to a metric space called the Brownian map, homeomorphic to the 2-sphere. And it turns out that this limit has Hausdorff dimension 4. So it's very fractal. Usually a surface has Hausdorff dimension 2, right? Well, this is Hausdorff dimension 4. And this was established in several works by Chassaing, Schaefer, Legal, Paulin, Bjormont. And it used important tool is bijections that encode the surface using a pair of trees. So here's a picture that my co-author, Jason Miller, drew, where you take a planar map and you have a tree. Well, this is a tree in the structure where you kind of color the vertices of each quadrilateral blue or red in a bipartite way. And then for some quadrilaterals, I can join the opposite things by, if I have 2 guys on the opposite the same quadrilateral, I can join them by an edge if I want to. Or if I don't want to, I can leave it blank. And then I can join the blues by a dual edge. So here's a tree. This is a spanning tree. It's a tree that each one of these quadrilaterals it crosses. And this is a dual tree where I include the whole boundary. So the boundary things were triangles. This is sort of thought of as one edge, so triangles in that sense. And then I have kind of a tree and a dual tree together. And then you can imagine taking a path that snakes in between the tree and the dual tree. So each it kind of hits these remaining white edges in order. And that's like a space-filling curve. And this was done using using something called circle packing. So for every triangulation, there's a unique way to map each vertex to a circle and put it in this way so that the vertices are the centers of the circles. And the circles are packed. So you have 3 of them meeting together everywhere. All right, so this is Ken Stephenson's circle packing algorithm. If you ever want to visualize a planar triangulation in a nice way, you can. This is open source software you can get online. Okay, and here, well, I've showed that now they're colored according to the time in which the circles are visited by the space-filling path. And I hope this looks at least roughly, vaguely reminiscent of that SLE curve I showed you. So this is now a space-filling curve. Okay, and this is just done by saying, okay, choose a random pair of trees, kind of glue them together to make a planar map, and then embed them with this circle packing and see what happens to this thing. Well, it kind of looks like that SLE curve we saw before. And is that actually happening in the limit? And what's going on here? Okay. Well, before I answer that, let me tell you about random surfaces. So how many of you have seen these pictures before? David Gu's conformal maps. A few of you. So he, at the time he did this, he was a postdoc at Harvard working with S.T. Yao. And so I guess they jointly came up with the idea of putting together, taking these classic works of Greek sculpture. This is the head of Michelangelo's David. And I mean, up till this point, I'm not aware of anyone having explicitly done a conformal map from Michelangelo's David's head to the sphere. But it was clearly calling out to be done. And so there's a conformal structure up here, and if you map it to here in a conformal way, so it's locally angle preserving, the image will look something like this. Okay, and this is now, obviously what I'm going to tell you in the next couple minutes will overlap a lot with what Alice told you in her talk, except that mostly I'm dealing now with 2-dimensional manifolds instead of 4-dimensional manifolds, which makes a number of things easier. So here, if I give you any surface, the Riemann uniformization theorem says you can take a conformal map that maps it to a flat surface. If I take a region here, it'll get mapped to some region down here. And I can take, we call isothermal coordinates. So if I'm for here, I can write the metric as, well, say the e to the rho of z, dz, or I guess the metric you can think of as being e to the rho z dz, where dz is Lebesgue measure down here. And this, this is exactly what came up in Alice's talk. But here, this rho z will be any real valued function, and then e to it will be a positive valued function. Okay, and you can kind of see if rho is equal to 0, you get the same surface back. If the Laplacian of rho is 0, then rho is harmonic. It's a flat surface, and generally the Laplacian tells you something about the curvature, the Gaussian curvature. So that if you integrate the Gaussian curvature over a region, that will be like integrating that will, of course, be like integrating the Laplacian of this over that same region. What encodes the Gaussian curvature. And if you think, well, if I want to take a random manifold, then I'd want to take this rho to be somehow random. And so what's the natural way to take a random manifold? So I want to take sort of a perturbation of a flat manifold. So something that kind of wants to be flat, but it has noise that makes it not flat. Well, it turns out there's an object called the Gaussian free field that kind of fits that bill. So the Gaussian free field is, let's see, how many of you have seen the Gaussian free field before? Is that? Okay, so about maybe 20% of you. Good, so the remaining 80% get to learn this today. So it's the Gaussian free field is a kind of a 2-dimensional analog of Brownian motion. Okay, I don't mean Brownian motion drawn in 2 dimensions. I mean the domain is two-dimensional. So Brownian motion is a map from the reals to the reals. And this will be a map from two-dimensional space to the reals. And the way you can think of it is you start out with a grid. And how would you take a random map from that grid to space? Well, there's a measure on functions, hd to r, where the density with respect to Lebesgue measure is, well, some constant times e to the sum over all edges in the graph of the height difference squared. Okay, times this minus 1/2 thing. So this here is a quadratic form, so if I take e to the minus 1/2 times that, this is giving me a Gaussian, right, of some sort of Gaussian random variable. And, okay, and that's what we call a Gaussian free field. This sum over height difference squared is what we call the Dirichlet energy. And if you think about it, if you had a box spring mattress, a mesh of springs, and I go through and I say, okay, pull each of the springs up to some height. This encodes the amount of energy it would take for you to do that. Okay, it's the sum of the squares, just by Hooke's law. And if I ask, choose a random, shake up your box springs. You can do this with if you have an old spring mattress at home, shake it up. And you can imagine if you're, following your Boltzmann statistics, you have your Gibbs measures, then you'd have some sort of your probability of like e to the minus this energy, okay, times some constant. Okay. And so now, the limit, you get a continuum object where somehow there's a continuum notion of Dirichlet energy, or the Dirichlet inner product, or just the integral of the dot product of the gradients. So the Dirichlet energy will be basically the L2 norm of the gradient. And you kind of want to say choose a random function where the probability of a function is e to the minus this Dirichlet energy. Okay, and you can kind of make sense of it in the continuum, maybe as a limit of these discrete guys. Or you can expand it in a basis. There are different ways of making sense of the continuum object. But the important thing is that the continuum Gaussian field has a conformal symmetry that the discrete one doesn't have. So if I take a conformal map from basically this Dirichlet inner product is invariant under conformal maps. If you think about it, if I take this Dirichlet energy, it's the L2 norm of the gradient, if I scale my domain this way by a factor of c, what happens? The area gets multiplied by c squared, right? But the gradient goes down by a factor of c, which means the gradient squared goes down by a factor of c squared, and these things cancel. Okay, and that's basically the fundamental reason that that in 2 dimensions, this gradient of this Dirichlet energy of the Laplacian is conformally invariant, and that's not exactly true in other dimensions. Okay, and if you want to know what's true in other dimensions, you can review your notes from Alice's talk. And while you're reviewing those notes, you'll read the part about determinant Laplacians. So you can imagine, like, I take these planar maps, and for every planar map, I could say maybe tell you how many edges there are in it and the log of how many spanning trees it has. So why does that matter? Well, so on a discrete graph, you can define the determinant of the Laplacian of the discrete graph. And it turns out that counts the number of spanning trees of the graph. Okay, so if you haven't quite worked through what the determinant of a Laplacian means on any space, you know what a spanning tree is. So it's the number of spanning trees. That's a well-defined object that we all probably care about. So the number of spanning trees, it tells you something about the graph, right? And if I give you a planar graph, what does the number of spanning trees tell you? Well, it kind of tells you how, well, I don't know. If I give you a map in the plane, what kinds of maps have very few spanning trees? Connected graphs. Trees, yeah. So tree, if I give you a tree, it has only one spanning tree itself, right? If I give you something with a lot of cycles, other edges, it will probably have more. So if I give you a grid, it's probably got a lot of spanning trees. If I give you a tree, it has very few. So you kind of think the number of spanning trees kind of tells you how tree-like a graph is. So it has very few spanning trees, okay, small determinant Laplacian, that's tree-like. Big determinant Laplacian, not tree-like. So think of determinant Laplacian as sort of encoding you, telling you how tree-like your surface is, okay? And it turns out that the Laplacian determinant to the minus 1/2 tells you the partition function of the Gaussian free field on the graph. So in some sense, it's, well, a continuum version of counting how many free field instances you can put on the graph. If I want to color the graph, give a number to each point on the graph where the number differs by a small amount from one edge to another. If the thing is a tree, then I have complete freedom in doing that. If the thing is not a tree, it has a lot of short cycles, then I don't have much freedom. Okay, and so it turns out the Laplacian determinant to the minus 1/2 counts this free field partition function. And if I were to choose a planar map together with an embedding in c-dimensional space, I'd want the probability of that map to be proportional to the Laplacian determinant to the minus c/2. And this is the idea that motivated Polyakov and others already back in late 70s, early 80s to think about this. Okay, and other kinds of statistical physics models are supposed to correspond to other c values. So now let me get to Liouville quantum gravity. So Liouville quantum gravity is going to be this model for describing a random surface. Okay, so in case you've lost track of where we are in the talk, I told you what a random tree was, I told you what a random path was, and I'm midway through telling you what a random surface was. But we had kind of a long detour into determinant Laplacians and Gaussian free fields and various things. But finishing this, what I do is I take that rho to just be some constant times the Gaussian free field. And so my free field measure will be e to the gamma h of z dz. That would be like the measure. And this is motivated by Polyakov. He wanted to say what happens when you take a random surface and then you weight by the determinant Laplacian. You should change from something more tree-like to less tree-like. There should be a family of random surfaces. And he said, well, that should correspond to just changing this gamma. As you tune gamma, it should become more tree-like or less tree-like. So when gamma is 0, you just get a flat surface. When gamma is large, you get a rougher, more tree-like surface. And he was motivated by string theory because you can think of the time evolution of the string as being a two-dimensional surface embedded in four-dimensional space-time. Okay, so if he wanted to integrate over the space of strings, string trajectories, he needed a measure on two-dimensional surfaces. Okay, so that's where he started thinking about this. And the measure is just going to be this e to the gamma hz dz. But how do you actually define that? Because if you think about it, it turns out that this function, this hz, this Gaussian free field, is not actually well defined as a function. It's a random distribution. So if you want to define e to the gamma h of z, this is, well, how do you take e to a distribution? You have to think about it, what that would even mean. But it turns out that already Hugh Krohn, in 1971, had worked out a way of constructing this measure. Okay, for unrelated reasons, he came up with this. And also someone named Kahan developed a whole theory of how you would exponentiate a free field and come up with this measure. By the way, Hugh Krohn was the PhD advisor of Helge Holden, whose name is the one you see on all these Abel Prize books that are getting passed around. Okay, so he's a great Norwegian mathematician who's played a huge role in this theory. And, well, I mean, a huge role in a lot of things. A huge role in this, in the Abel Prize stories. And anyway, and so it doesn't make literal sense, but you can, these pictures I'm showing you here are an effort to try to draw partition space into squares that all have about the same size in this random measure. Okay, so basically the way I do this, I start with a square, I cut it into 4, I cut those into 4, I cut those 4, and if I ever get to any point where the square has area less than delta, for some fixed constant delta, I stop subdividing. Okay, and so I pick the random measure, I subdivide this way, and I get these squares that all have about the same size, in the sense that their dyadic parent with size bigger than delta, but they have size smaller than delta. So you think of their size as being about delta. Okay, and the place where here we have lots of little squares, that's a high density region for the measure, and here's a small low density region. Okay, and you can see that as I make gamma bigger, the discrepancy between the low density regions and the high density regions gets larger. Okay, so this here is maybe, New York City, and this out here is, the Great Plains. This is Iowa, and maybe this is Pittsburgh, some smaller city here. So this is a landscape where most of the mass is in these regions that are kind of fairly small, and most of the Euclidean area belongs to fairly wide open spaces. Okay, and I want to, before I go on, tell you about there was a fairly recent set of papers, a series of 6 papers that shows that if you take a uniform random planar map, so the uniform measure among all triangulations, and you map that into the plane using something called the Cardy embedding, which is a variant of that circle packing thing. I won't tell you exactly how it works, but you embed it in the plane in this proper way, and then you take the limit as the number of quadrilaterals goes to 0, then the measure that you get here converges in the limit to the Liouville quantum gravity measure. Okay? So you take this random planar map, embed it conformally into the plane, take the limit, and you converge to this e to the Gaussian free field measure. Okay? And this was established in a series of 6 papers by, does anybody know who wrote these 6? So I'll give you a clue. One of them is the niece of Helga Holden, Norwegian mathematician. That's Nina Holden. This was proved by Nina Holden and Shin Sun. So Nina just got her PhD in 2018, and Shin a couple years earlier, and they've been working on these things for quite a while. And there are a couple other co-authors who've been on one of these other, on some of the papers. But it's kind of a huge undertaking. They've managed to actually prove that random planar map embedded this way, you really do get, in the scaling limit, exactly this Hug-Krohn measure that was already introduced in 71. So Nina, I think, is not much older than Abel was at the time he died. So this is just another case of young Norwegian mathematicians doing impressive things. Random growth models, the next topic here, is so if I give you any planar map, you can imagine putting a random distance function on it by, say, assigning to every edge a random weight. Okay, and then the distance between 2 points is sort of the shortest weight path between them. And now I can I can graph points according to their distance from the origin. So here they're colored according to how far they are from the origin in this random weight. Okay, and this is the growth model that tells you how this grows in times is something called the Eden model. And this has kind of a whole theory behind it. But I want to point out that there is a certain way to formulate this model that's maybe not so obvious, where you just say, grow your cluster one vertex at a time. Each time I add a new cluster, I look at all of the edges that connect blue to red. I pick one of them uniformly at random, and then I color the opposite vertex of that blue also, so both endpoints are blue. And so I'm basically growing this way. And this was introduced by Eden. He was thinking about modeling the growth of a cancer cell. So you think you've got a cancer cell, there's some interface between the cancerous region and the healthy region, and you kind of pick a random point along the boundary of that region to decide which the next place would be where the cancer will expand into the healthy region. And this might be some sort of model for how cancers would grow. But there's a variant of this where you could imagine that you grow by adding a point. Instead of just picking uniformly on the boundary, I take a point walking all the way from infinity, and when stop it when it hits the boundary. And that's what we call DLA. And you get these pictures like this, where a point wanders from far away and it hits this. And you can imagine this is like a snowflake. Imagine this is a simplified model for a snowflake where you're in a very low moisture region. And so it's sitting up there collecting no moisture, and then one particle of moisture wanders in from far away, and then it glops on at some random point. So it does a simple random walk until it hits the existing crystal, and then it glops on right there. And then if things were coming one at a time and doing this, then it would grow into some sort of snowflake-looking pattern. Okay, and you can imagine manganese oxide patterns growing on surfaces of rocks, or put like a bolt of lightning through a thing of plexiglass. There's some reasons they think this might correspond to DLA. And it's something that, it has, I think by this point it has like 17,000 papers written out about it on Google Scholar. And nearly all of them are in physics or computer science. There are very few in math, relatively speaking, because it's very hard to prove theorems about. It's something where if you have a computer, you can write up the code to simulate a version of it in about 5 minutes. But if you want to prove even the very most basic theorems about it, you can spend years and get nowhere. And many people have. But what we found is there's certain, so even the basic things like, is there a scaling limit of this? Is it random at large scales? These are things that we haven't been able to prove, and we still don't know. But what we do know is something about what happens when you do DLA on a random planar map. So it turns out that there's a continuum version of DLA on Liouville quantum gravity surface that we can define. Okay, so I'm going to very quickly tell you about this drama. So how all these various objects are connected together. Okay, so first of all, right, if I take any field H, I can define a vector field by taking e to the IH and interpreting this as a complex unit vector. And this is positioning a complex vector like that at every point in space, and then trace the flow line of that. And if I add a constant to that ray, that's like rotating all the arrows 90 degrees and tracing a flow line of that. And so the rays of this create some structure. And it turns out that if I take H to be the Gaussian free field, these curves become forms of SLE. You can make sense of it. And so these are what these curves look like. These are all of different angles, SLE. And these are curves starting at the center where I add like a logarithmic singularity to the field, which makes the curves spiral around. I'm going to take a bunch of curves all flowing northeast. And it turns out that these curves kind of merge into each other. So they start to form kind of a tree structure. I take the northwest curves going a different direction, where I add a constant to my field and go that direction, I get a different structure. It turns out that these tree structures are related to these SLE curves, where if I were to start from every point and draw the curve from that point, I would get kind of a space-filling tree. And if I draw the boundary of that tree, I get a space-filling curve, which is another form of SLE. So this will be SLE some kappa, and then the space-filling version will be SLE 16 over kappa. So one is less than 4 and one is bigger. Okay. This is something called, I can use these curves if I look at the light cone, the set of all points I can get to starting at one point, or the set of all points I can get to by going sort of left or right from one point turns out to trace out one of these SLE curves where kappa is between 4 and 8, a curve that bounces off itself. Okay, here's one of these. They're like these two trees glued together. This is one of these space-filling curves. Jason Wheeler actually won an art competition for this, a mathematical art competition. This is one of the, or something like this was one of the works. And so, next thing what we discover is that if you take two of these random surfaces and you glue them together and conformally map the result to the plane, the interface between the curves becomes an SLE curve. So, so if you take two canonical random surfaces, glue them together, conformally map it, the interface between them becomes an SLE curve. Okay? So this is one of the punchlines, I hope you appreciate it, of the talk, is that surface plus surface equals a surface with an independent SLE curve drawn on top of it. And it turns out if you take two of these space-filling trees and glue them together, what you end up getting is a curve with a space-filling, a sphere with a space-filling curve on it, and that's the measure you get becomes one of these Liouville quantum gravity measures, and the interface becomes one of these SLE curves. Okay.
So can I take more than two together? Is that
You know, I've thought about that, and I haven't really been able to come up with a great story for it. But we can talk about that afterwards if you want. It's an interesting question. But certainly, I mean, topologically, you can do it, right? You get some quotient space. I just haven't been able to come up with an interesting story about what it means. But two things, you know, here you take two trees, you know, you glue them together and you get a sphere. And well, I want to say that if I take my two hands and I think of the boundary, this as being the boundary of a tree, my hands are correlated with each other. So when I glue the boundaries together, it looks kind of just like a tree itself. So it turns out if you take two Brownian motions that are correlated with each other and use that to define a tree, then you get something that will be more of a flat surface or more of a tree-like surface. If they're anti-correlated with each other, like my hand and my hand slightly shifted, then it gets something that's closer to a flat surface. So tuning this correlation takes you from more tree-like to less tree-like. And actually, as you change the correlation from perfectly correlated to perfectly uncorrelated, you span this entire set of Liouville quantum gravity measures from the flat surfaces to the critical point. So all of these Polyakov surfaces are obtained by gluing together pairs of trees, which they had no idea at the time that they could be described in this way. Now, it turns out that if you take a tree of Liouville quantum gravity bubbles and you glue it to another tree of Liouville quantum gravity bubbles, the boundary between them becomes one of these SLE kappas with kappa between 4 and 8. And it turns out that if you take a growth model on a surface, like you do one of these Eden models on a Liouville quantum gravity surface, or you do a DLA on a Liouville quantum gravity surface, then provided the type of DLA, you choose the type of Liouville quantum gravity surface correctly, then we get an object that we can describe in the continuum. So, so maybe this is a good place to end. So I just want to say that we actually, you know, despite the fact that we still do not understand DLA, the limit of DLA in the plane at all, we now actually can tell you what DLA is, what the limiting object should be in some sense on this, on a Liouville quantum gravity surface. Okay, so that's it. Yes?
Is it a general thing that we learn from that some statistical physics models are easier on the random surface than on the plane?
Yeah. So, you know, there's some things about this analysis that becomes much easier on random maps, and some things become harder. So, you know, one thing that becomes easier is that if I take a random planar map decorated by a path and I say take uniform measure on the set of path-decorated planar maps with, two marked vertices or something. Then if I set the model up correctly, then these two sides will be independent of each other once you're given the length of the path and the area of the two sides. And so this sort of independence between the two sides, that you can forget this side and resample it without knowing what this side is, that simplifies life tremendously. Whereas if I said take a random self-avoiding walk on the grid, well, once you see this side, you know the other side. So you don't have anything like that kind of independence. And so these sort of properties, sometimes they really help you a lot. And you're very, very happy that you're working on a random planar map instead of a grid. There are other times, of course, where the random planar map gives you all kinds of headaches because you can't pin it down and the shape is varying along with, so some things are harder and some things are easier. But I would say there are a lot of combinatorial symmetries that make these models simpler. So for example, this self-avoiding walk is supposed to approximate some SLE curve on a grid, but it's still not proved. We still don't know that it approximates an SLE curve. But thanks to work by Jason Miller and Ewan Gwynn, we now know that these random walks, that this path on a random planar map, when you embed it the right way, it does converge to SLE 8/3. So there's some things that are still hard here that are known here, and of course the other way too, because I don't need to tell you why the grid is simple to work with. It's simple in a lot of ways, but this basically it's these nice Markovian properties that make this friendlier.